Hello, my name is Jiajia Li. I come from Computational Science and Engineering, Georgia Institute of Technology. The project is about the study of basic tensor operations from linear algebra to multilinear algebra. This is a joint work between two research groups, HPC Garage and SunLab. HPC Garage is led by my advisor, Professor Richard Woodcock. His research focuses on high-performance computing. SunLab is led by Professor Jimeng Sun. His research focuses on data mining and machine learning for health applications. Let's see some background first. Big data emerges in many real-world applications with two features, large scale and high dimensionality. High dimensionality means there are many attributes in the data. Many application domains generate large-scale data, such as quantum chemistry, quantum physics, signal and image processing, neuroscience, machine learning, and healthcare analytics. Tensors can be interpreted as multidimensional arrays. We draw two three-dimensional tensors here. A tensor provides a natural and compact representation. Each dimension of it corresponds to an attribute from real-world data. So the left figure is a dense tensor. That means each entry in the tensor is the non-zero. The right one is a sparse tensor, means most of the entries in the tensor are zeros. Only the dark spots represent the non-zero elements. Usually, we use compressed format to store a sparse tensor. As we know, linear algebra is fundamental in scientific computing, machine learning, data analytics, and so on. In linear algebra, the basic operations are matrix and vector operations. And the other algorithms also include LU factorization, QR factorization, and so on. Multilinear algebra is an extension to linear algebra, which focuses on tensor operations and tensor algorithms. The motivation to introduce tensors into real-world applications are as follows. Tensors are better to represent relationships between each data attribute. For example, we can draw a three-dimensional tensor from healthcare application using three attributes: patients, diagnosis, and medications. Generally, for a single patient, there are more than one diagnosis and many medications. The relationship is simple to represent in a tensor, but by using a matrix, we need many rows or many records to represent this relationship for a single patient. That increases the computing work for data analytics. After build a tensor, we can use tensor algorithms to exploit existing or even hidden domain knowledge on it. My work focuses on optimizing basic tensor operations by considering both the characteristics of computer architecture and the input tensor features. Tensor operations include tensor matrix multiplication and several types of tensor products. The characteristics of computer architecture is the major consideration for high-performance computing area. We consider register size, cache size, memory behavior, and three types of parallelism for tensor algorithms. The three types of parallelism include multi-threading, distributed parallelism, and co-working accelerators. The input tensor features include tensor dimension, tensor shape, sparsity, and so on. Using the optimized tensor operation, we can improve the build-on tensor algorithms. My work focuses on tensor factorization, such as CP and Tucker decomposition. There are three challenges for tensor algorithms. The first is the sparsity problem. A sparse tensor has irregular distribution of non-zero elements. This sparsity introduces high cache misses and high memory or network communication, which are very time-consuming. The second is the indexing problem. The dimension size of a sparse tensor exceeds the range of normal integers, although we can store a very large sparse tensor in memory. In this case, we need to increase the indexing range. That will create several times higher memory consumption, which is a very critical issue to big data storage. The last challenge is dimension-sensitive nature, which means a single tensor operation on different dimensions will generate non-uniform program behaviors. This nature causes irregular memory accesses, prevents data tensor operations from achieving close to peak performance as traditional dense matrix operations. I have made some progress on the project. I published a paper about dense tensor times matrix multiply on a supercomputing conference last year. I also finished a survey work with other people. The ongoing work are as follows. The first is to optimize matricized tensor times cartridge product for CP decomposition, and another is the study of sparsity features. To summarize, because of its broad applications and challenging research problems, Tensor Project is very worthy to be supported. Thank you very much for your attention.